Okay, so this video follows directly on from the previous one where we introduced the solving of trig equations, and now we want to make things a little bit more complicated. So you'll recall I said to you in the last lesson, the simple equations is where there was nothing happening in here. In these examples, we're going to have sine of 2x, cos of 3x, sine of x plus pi on 3, cos of 3 times x minus pi on 4. Okay, so we want to think through what do we do when there's a bit more going on in there, and we do need to think about a couple of things. So I'm going to, before I go through these examples in here, I'm just going to detour and go back to the equation that we started with the simple equations. Let's think about the equation sine of x equals 1/2. Okay. Let's just revise how we solve that, and then I'm going to alter that slightly, and then we're going to go back to the examples. So we know that sine of x equals 1/2, okay? So the first step is to get the sine or the cosine on its own, which it already is. The next step is to think about your exact values, and you'll remember when we're thinking about sine being equal to 1/2, our special triangle is the half and equilateral triangle. If sine is equal to 1/2, this has to be the opposite side, and this has to be the hypotenuse, and so therefore we must be talking about this angle up here, which is pi on 6, or 30 degrees. Half the equilateral triangle. Okay. Alright, so all our solutions are connected to pi on 6. Then we go to our unit circle. Where are the solutions in the unit circle? In this instance, sine is equal to positive 1/2. Sine is positive in the first and second quadrants, and so the location of all our solutions is here and here. The next thing we think about is our domain. Let's say this is just between 0 and 2 pi. Okay, so 0 to 2 pi, starting at 0, one lap around to 2 pi, we find two solutions, and we get that x is equal to pi on 6, or 5 pi on 6. Okay, what I want to do now is change this equation very slightly and say, okay, what if it's sine of 2x equals 1/2? And we want solutions between 0 and 2 pi. Okay. Now, what we need to understand is when we get the solutions out of the unit circle, whatever we find here, they are the values that go in there. Okay. Sine of something equals positive 1/2, or sine of pi on 6 equals positive 1/2. Sine of 5 pi on 6 equals positive 1/2. Sine of, what's the next one going to be? 13 pi on 6 equals positive 1/2. Sine of 17 pi on 6 equals positive 1/2. Okay, so whatever comes out of the unit circle is equal to whatever's in the sine function. And so logically then, all those same processes apply, but now it's not x that's going to be equal to pi on 6 and 5 pi on 6. It will this time be 2x that's equal to pi on 6 and 5 pi on 6. Okay? And then these are just linear equations. This is essentially, I want you to see this as this, you don't need to write this, but this is essentially 2x equals pi on 6 or 2x equals 5 pi on 6. And so they're just linear equations. You want to solve for x, you're going to divide by 2, and so you're going to get x equals pi on 12 or x equals 5 pi on 12. Okay? Now, I don't want to write it out like that. It's going to get crowded, particularly when we've got 8 solutions, for example. So we're simply just understanding that to solve for x, we're dividing both sides of the equation by 2, and so we get pi on 12 and 5 pi on 12. Sorry, that's x. We've divided everything by 2. Okay, what I want to do is I want to solve this equation with my CAS and see what happens. So menu 3.1, we're going to solve sine of x equals 1/2 for x, but we want to just find the solutions between 0 and 2 pi. So remember, outside your sine function, given that 0 is less than or equal to x, which is less than or equal to 2 pi. Oh, sorry, that was my original equation. We already got that. Sorry, our new equation was sine of 2x. Now, we've got the two solutions we found, pi on 12 and 5 pi on 12, but there are two additional solutions that we didn't find. There should also be 13 pi on 12 and 17 pi on 12. Okay, I'm just going to jump across to a graphing program because I want us to think graphically about what happened, what the difference between these two equations is. Okay, so let me just pause the video a moment while I change programs. Okay, so here we are here, and I might, yeah, I'll leave the window as it is. We're seeing quite a lot of the graph here where we just want to focus between 0 and 2 pi, but let's be clear about what's happening. Actually, no, I might just adjust it to be 0 to 2 pi. Just give me 1 second. Let's make that a 2. Okay, and let's get rid of that. Okay, so let's just focus on that. So what we're seeing here, hold on, let me just get my label back in so we can see the equations. Okay, so we've got it here. Now we're looking between 0 and 2 pi. The red graph is y equals sine of nx, but at the moment n is 1, so it's just y equals sine of x. And we've also got y equals 1/2. And we've got our two solutions that we're familiar with. Let me just mark them here. Again, the pen in this program is very hard to draw accurately with, but we're looking at our first solution there, which we already know was pi on 6. And we're going to have our second solution there, which we know was 5 pi on 6. So what this graph is showing us is solving sine of x equal to 1/2, which we've done. What I want to look at is what changes when we're looking at sine of 2x equal to 1/2. And let's think about what that does to the graph. So sine of 2x equal to 1/2 means I'm just going to now use this constant controller to change the value of n. So I'm just going to increase it. Now it's 1.5. Let's make it 2. Okay, so now what we're seeing here, I've left the black graph, so that's still the intersection points between the black graph and the blue graph are still where sine of x equals 1/2. But now the red graph is sine of 2x. Okay, so the intersection points between the red graph and the blue graph are the solutions to sine of 2x equals 1/2. So what happened here, let's think about the process of what making this 2 does. That's a dilation from the y-axis by a factor of 1/2. We've squashed the graph in by a factor of 1/2. All of the x values have been halved. So this solution that was at pi on 6, when the equation was sine of x equals 1/2, has now moved in here to half of pi on 6, pi on 12. We found that solution ourselves. This solution here is now this one dilated in by a factor of 1/2, and that is now at half of 5 pi on 6, so that is 5 pi on 12. Again, apologies for the poor handwriting in this program. So they're the two solutions that we found. I also don't know how to change the pen colour, to be clear. So these are the two solutions we found when we did sine of 2x equals 1/2. But what we missed is that also within this domain, still from 0 to 2 pi, there are two further solutions to this equation down here, which we saw in our CAS, but which we didn't find ourselves. And that's because when we found the solutions out of the unit circle, where we were essentially just solving sine of x equals 1/2, we only looked between 0 and 2 pi. And so we found all the solutions between 0 and 2 pi, but then we halved them. And so actually what we ended up with was actually the solutions between just 0 and pi. So these two solutions here, they came because of the dilation, and they were out between 2 pi and 4 pi. So let me just remove all my annotations for a second while I change, while I change the window. Let me just pause while I adjust it to show you what actually happened. Okay, I actually don't need to remove my annotations because I can just change the window and they'll move with it. So what we're looking at here is these couple of solutions here, where did they come from? And they came from that dilation by a factor of 1/2. Okay, so let me just adjust the window now. Let me move from looking just between 0 and 2 pi, and let's look between, just let me delete the 2 and make it a 4. Okay, so these two the eraser on. These two solutions here, now again, I know it's getting messy here, but they were these solutions to when sine of x equals a half between 0 and 4 pi, so that then when we halve and halve, they end up between 0 and 2 pi. Okay, so what we need to do, I know that got a bit messy, but the idea is that when you change the sine of x equals a half to sine of 2x equals a half, the parts of the graph that were between 0 and 4 pi all get squashed down to now fit between 0 and 2 pi. So when you're in the unit circle, you need to look for all of the solutions between 0 and 4 pi so that when you halve everything, you've got what you need. And we can do this by thinking through the adjustment to the domain that needs to happen. So let me go back over to the original notes. Okay, so what we need to do is we need to make adjustment to our domain. So we need to understand that at this final line of working here, we want x to be between 0 and 2 pi. But at this line of working, where I am finding my solutions out of the unit circle, I'm not solving for x, I'm solving for 2x. So if x has to be between 0 and 2 pi, 2x, which is double that, is going to have to be between double 0 and 4 pi. So I have to find the solutions. If I'm finding solutions for 2x, they're going to need to be between 0 and 4 pi, so that then when I divide by 2 in the last step, I will have all of the solutions that are between 0 and 2 pi. So actually, at this line here, this blue line that I've encased in blue, I should have found all the solutions between 0 and 4 pi. So I should have done a second lap of my unit circle. And I should have found 2 pi plus pi on 6, which is 13 pi on 6, and 3 pi minus pi on 6, which is 17 pi on 6. So that then, when I divided everything by 2, I now have solutions that are all between 0 and 2 pi. And you should be able to check that. Obviously, this is bigger than 0. 2 pi would be 24 pi on 12. And so therefore 17 pi on 12 is definitely within that range. Okay, so we really need to think through that adjustment of the domain. So we find all of the correct solutions from the unit circle, and then we bring that, and then when we just do the last algebraic manipulation, we then have the solutions that are within the required domain at the end. Okay, let's have a look at the examples. Sorry, I hope that didn't get too convoluted there. So process is still the same. Step 1, make sure you've got the sine or the cos on its own, or the tan when we get to tan equations. Step 2, use your exact values to determine the reference angle. Step 3, determine the quadrants where your solutions will be. Step 4, again, is about domain, but here you want to adjust the domain as necessary. Now, you're not changing the domain of the function. X still has to be between 0 and 2 pi. But what does that mean for 2x so that I can then find the solutions I need? And then finally is to rearrange to solve for x. Okay, so let's work through that. First step is going to be to get the sine on its own. So we just need to divide both sides by 2 here. So we're going to have, sorry, I'm just going to move that over a bit. We're going to have sine of 2x, is equal to negative root 3 on 2. Okay, we need to think about our exact values. Root 3 on 2 is what's important here, the fact that sine is equal to root 3 on 2. The negative is about the quadrants. So root 3 is in the special triangle that's half an equilateral triangle. Okay. We want sine to be root 3 on 2, which means the root 3 needs to be the opposite side, and 2 is the hypotenuse. So therefore, we must be talking about this angle down here, which is the 60-degree angle, so pi on 3. So all my solutions will be connected to pi on 3. Then I want to think about my quadrants. So sine is equal to a negative value. Where is sine negative? Let me just move these notations on the side here out of the way so that we've got just a bit more room. Just going to move them over a bit. Oh, sorry, I lost that as well. Okay, let's just move that out of the way. Okay, so sine is equal to a negative value. So in terms of quadrants, sine is negative in the third and fourth quadrants. Solutions we've decided are connected to pi on 3. So pi on 3 down here and pi on 3 down here. So pi on 3 is not a solution in this instance. Pi on 3 is in the first quadrant. So it's important that you don't write that x equals pi on 3 or that 2x equals pi on 3. I also don't want to see, something I see really commonly is that root 3 on 2 equals pi on 3. These things aren't equal to each other, okay? Root 3 divided by 2 is about 0.86, and pi divided by 3 is about 1.04. They're not at all equal to each other. So please be careful about what you write, okay? Sine of pi on 3 is equal to root 3 on 2. If you want to write that from here, fine. Sine of pi on 3 is equal to root 3 on 2. We now want to think about what does that mean for sine of 2x equal to negative root 3 on 2, okay? Alright, so we've located our solutions. Pi on 3 in the third and fourth quadrants. Okay. Next thing we want to think about is that out of the unit circle, whatever solutions come out of here are going to be equal to 2x. Okay, they're going to be equal to whatever is in here. Okay, so if they're all going to be equal to 2x, okay, we're then going to need to divide them all by 2 to find what x is equal to. So we want to think about adjusting our domain. So we know that at the end here, we want x to be between 0 and 2 pi. So therefore, at this line above, I'm not solving for x, I'm solving for 2x. So 2x is twice as big as x, so therefore let's also double 0 and let's also double 2x. Okay. So we're multiplying 2 to work back that way for the domain, because ultimately we're going to want to divide by 2 when we come in this direction. So we need the domain to be, the domain is still 0 to 2 pi, because domain's about x. But when we take the solutions out of the unit circle, we need to find all the solutions between 0 and 4 pi to make sure that we have everything we need. So that then when we divide it all by 2, it'll all be between 0 and 2 pi. So we're going to start at 0. We're going to do one lap around, so that's pi, continuing around to 2 pi, continuing around again, that's now 3 pi, and finally around to 4 pi. So if we get all the solutions between 0 and 4 pi out of the unit circle, divide them by 2, they'll all be between 0 and 2 pi. So 4 solutions. My first solution is here in the third quadrant at pi plus pi on 3. So pi is 3 pi on 3 plus pi on 3, that's 4 pi on 3. My second solution is around here in the fourth quadrant at 2 pi minus pi on 3. 2 pi is 6 pi on 3, minus pi on 3 is 5 pi on 3. My next solution is around again in the third quadrant at 3 pi plus pi on 3. Okay, so 3 pi would be 9 pi on 3 plus 1 pi on 3, so that is 10 pi on 3. And then my final solution is in the fourth quadrant at 4 pi minus pi on 3. So 4 pi is 12 pi on 3 minus 1 pi on 3 will be 11 pi on 3. Then we're going to divide all our solutions by 2 to solve for x. When we divide a fraction by 2, we double the denominator. Okay, so in this case, they're going to all become over 6. So 4 pi on 6, 5 pi on 6, 10 pi on 6, and 11 pi on 6. We then need to make sure any fractions are in simplest form. If you can do that as you go, fine. But if you'd prefer to get them all over 6 and then worry about any simplification, we need to do that. So 4 on 6 will simplify and 10 on 6 will simplify. And so we're going to have 2 pi on 3, 5 pi on 6, 5 pi on 3, and 11 pi on 6 are our 4 solutions to this equation. We should be able to verify that with our CAS. If we solve this, menu 3.1, if we solve 2 times sine of 2x equal to negative root 3, negative root 3, if we solve that for x and we give it the domain from 0 to 2 pi, given that 0 is less than or equal to x, which is less than or equal to 2 pi, 2 pi, we indeed get 2 pi on 3, 5 pi on 6, 5 pi on 3, and 11 pi on 6. Okay, let's have a look at another one. So solve root 2 cos of 3x plus 1 for x between 0 and 2 pi. So let's focus first of all on getting the cos on its own. So let's subtract 1 from both sides and divide both sides by root 2. Then we want to think through our exact values. I know that if root 2 is involved, it has to be about pi on 4. Okay, cos of pi on 4 is equal to 1 on root 2. So my reference angle is pi on 4. Cos is equal to a negative value, however, negative 1 on root 2. So that tells us about which quadrants our solutions should be in. They're still going to be connected to pi on 4, but they're going to be where cos is negative. So I'm just going to make that circle a bit smaller. Okay, so pi on 4 in the second quadrant and pi on 4 in the third quadrant where cos is negative. So pi on 4 and pi on 4. Okay, now then, remembering the solutions that come out of the unit circle are equal to that. What we are looking at is, doesn't matter what's in here, we're looking at cos of something equals negative 1 on root 2. We know it's going to be located in these two positions in the unit circle. Okay, so we need to worry about what we're finding here is going to be equal to, sorry, just lost my pens. It's going to be equal to 3x. So it's going to be 3x equals to Okay, I'm just actually going to move all that over because I'm going to run out of room, I think, to fit all my solutions in. Let's just move that over a bit. And then once we've done that, we're going to find that we're going to need to divide everything by 3 to solve for x. Okay, so again, let's think about our domain. We want x, so at this line, x is going to be between 0 and 2 pi. At the previous line though, when we're getting the solutions out of the unit circle, they're not equal to x, they're equal to 3x. And so if x is going to be between 0 and 2 pi, 3x is between 0 and 6 pi. So in the unit circle, we need to find all the solutions between 0 and 6 pi, so that when we then divide them by 3 in the final step, they're all between 0 and 2 pi. Okay, so we're going to start at 0. 6 pi is 3 laps of the circle, so we're starting at 0, we're coming around to pi, we're coming back around to 2 pi, around to 3 pi, 4 pi, 5 pi, and finally 6 pi. So 3 full laps of the unit circle, we're therefore seeing 6 solutions. So our first solution's in the second quadrant. It is at pi minus pi on 4. That's 3 pi on 4. Our next solution's in the fourth quadrant. It's at pi plus pi on 4. So that's 4 pi on 4 plus pi on 4. That's 5 pi on 4. Sorry, 5 pi on 4. My next solution is at right round again into the second quadrant. So 3 pi minus pi on 4. 3 pi is 12 pi on 4. Minus 1 pi on 4 will be 11 pi on 4. And so my next solution is at 3 pi plus pi on 4. So that's 12 pi on 4 plus 1 pi on 4, so that's 13 pi on 4. And then again, around again, 2 more solutions in the third lap. 5 pi minus pi on 4, so 5 pi would be 20 pi on 4, minus 1 pi on 4 is clearly 19 pi on 4. And then my final solution, 5 pi plus pi on 4, so that's 20 pi on 4 plus 1 pi on 4, so 21 pi on 4. Okay, so then we need to solve for x, which is to divide everything by 3, which will make all of the denominators 12. So we get 3 pi on 12, 5 pi on 12, 11 pi on 12, 13 pi on 12, 19 pi on 12, and 21 pi on 12. And then obviously we also need to make sure we simplify any fractions. So 3 on 12 will simplify, and 21 on 12 will also simplify. So that is pi on 4 5 pi on 12, 11 pi on 12, 13 pi on 12, 19 pi on 12, and 21 and 12 can both be divided by 3, so that is 7 pi on 4. And again, we should be able to check that they're all within the domain. Obviously that's bigger than 0. 2 pi would be 8 pi on 4, or it would be 24 pi on 12. So all of those solutions are definitely smaller than those. Okay, so we have all the solutions between 0 and 2 pi. Okay, let's have a look at examples 3 and 4. So this time we haven't got a dilation happening in here, we've got a translation happening. Okay, so again, let's think about that kind of graphically, remembering that essentially when we find the solutions out of the unit circle, we're finding all the solutions between 0 and 2 pi. Okay, but what we have here is, so this is y equals sine of x, okay, and this is y equals half. Okay, so we've already done this lots of times now, we get pi on 6 and we get 5 pi on 6. If I want to look at sine of x plus pi on 3, that's sine of x to the left by pi on 3. Okay, so I want to move this graph now to the left by pi on 3. Okay, and I'm going to get something like this. Obviously I'm just drawing it quite roughly. So in terms of thinking about the solutions, this solution here, translated to the left by pi on 3, is now here. It'll be at pi on 6 take away pi on 3, whatever that is. Okay, that would be pi on 6 minus 2 pi on 6, so that would be negative pi on 6. Okay, this solution that was here has now moved across, and that's here. That would be at 5 pi on 6 minus pi on 3, which is 5 pi on 6 minus 2 pi on 6, that's 3 pi on 6, or pi on 2. Now the problem is that this solution's now gone out of the domain if my domain is 0 to 2 pi. So the problem is I actually needed to think about the next solution and the original function. I needed to think about this solution up here, so that when the graph is moved to the left by pi on 3, that solution now comes into the domain. It wasn't in the domain, it wasn't between 0 and 2 pi, but it's going to come into the domain when I subtract pi on 3 from all the solutions in the process of moving left. This solution that was between 0 and 2 pi moves out of the domain and becomes irrelevant to the problem. Okay, so it's the same process in terms of what you're doing algebraically. It's the same idea that if you only look between 0 and 2 pi in the unit circle, after you then apply whatever transformation's happening, those solutions may move out of the domain and not be relevant anymore, and other solutions may move into the domain and you missed them by not thinking carefully about it at the beginning. Okay, so let me just try and move that a bit out of the way so that things don't get too crowded over here. Alright, let's just get rid of that for a minute. Okay, so let's still try and think through the same steps. Getting the sine or the cos function on its own, that's already happened. So we already have sine of something equals a number. Done. Next thing is to think about your exact values. So sine's equal to a half here. Okay, so half comes from this triangle. This would be the opposite, this would be the hypotenuse, so therefore we're looking at pi on 6. Okay, so our solutions are to do with pi on 6. Sorry, I'm just going to move that graph further over yet. We need the space. Okay, so solutions to do with pi on 6, because sine of pi on 6 is equal to a half. Then we need to think about quadrants. So sine of something, so it doesn't matter what's in here until later. Sine of something is equal to a half. Okay, we're thinking about where is that in the unit circle. That's all we're focused on right now. I'm not worried about what's happening inside there. So we've already established it'll be to do with pi on 6. If sine's equal to positive half, we must be up here in the first quadrant. What we're still thinking about is sine equals a half. Okay, in the unit circle, where is the y coordinate a half? Okay, it's not changing anything we've already learnt. So we know it's going to be pi on 6 up from here and pi on 6 from up from here. That's the location of my solutions. Okay, now I want to think about whatever solutions I get out of the unit circle, they're going to be equal to whatever's in here. Okay, so they're going to equal x plus pi on 3. So x plus pi on 3 will be equal to whatever. Okay, What we're then going to need to do to solve for x is to subtract pi on 3 from both sides. Okay, so subtract pi on 3 and we'll have our solutions. Now, domain, we need the final domain here. We need x to be between 0 and 2 pi. Let's think about what that means for x plus pi on 3 then. Okay, so if I add pi on 3 to x, I need to add pi on 3 to the other thing. So I actually need to find all the solutions between pi on 3 and 2 pi plus pi on 3. So that's 7 pi on 3. What I want you to notice is when we're adding, we're not changing how wide this is, okay? If this, from 0 to 2 pi is a span of 2 pi, from pi on 3 to 7 pi on 3 is also a span of 2 pi. It's not being stretched, it's just shifting, okay? So what we need to do is, out of the unit circle, we need to find all the solutions between pi on 3 and 7 pi on 3. Okay, so pi on 3 and 7 pi on 3 are both located about here in the unit circle, okay? So if that's pi on 3, 2 pi plus pi on 3 is also there. It's one lap away. So we're not starting at 0 here. We're starting up here at pi on 3 and doing one lap of the unit circle around to 7 pi on 3, which is 2 pi plus pi on 3. And there are two solutions in that interval, okay? But the first solution is not pi on 6. That's not in the domain. I might write that solution down. I'm just going to write it here in grey. Oops, sorry, in grey. Because I know it's going to be tempting to write that solution down, but I want to show you what will happen. I'm just going to write it there for now. And if you write it there, it's not going to be wrong. You'll realise it's wrong later on. But we want to try and focus on getting the right solutions out of the unit circle. So the first solution isn't 0 plus pi on 6 because we're starting at pi on 3. We're travelling around past the first solution to pi and then around to 2 pi and then to the next solution. Okay, so our first solution is this one, and it is at pi minus pi on 6. So that's 5 pi on 6. Our second solution is around at 2 pi plus pi on 6. So that is 12 pi on 6 plus 1 pi on 6. That's 13 pi on 6. Okay, now we're going to need to solve the equation. So again, I'm just going to write out a line here that I won't normally do. So what we need to picture here is, let's ignore that solution that shouldn't be there, the grey one. What we essentially have here is two equations. X plus pi on 3 is equal to 5 pi on 6, or x plus pi on 3 is equal to 13 pi on 6. And so to solve for x, we're going to need to subtract pi on 3. Subtract, so 13 pi on 6 minus pi on 3. Okay, so I don't want to have to write them out as separate equations. We simply understand that to solve for x here, we need to subtract pi on 3 from every solution. Okay, we're thinking about the fact that pi on 3 is 2 pi on 6, so we're subtracting 2 pi on 6. So if we do that for this first solution that we shouldn't have got first, if you subtract 2 pi on 6 from that, you get negative pi on 6, which is clearly not in the domain, which is why we didn't need to think about it first. But I know it will be quite common for you to write it, but when you get to this point, you'll realise, not in the domain. I don't need it. Okay, 5 pi on 6 minus 2 pi on 6 is 3 pi on 6. 13 pi on 6 minus 2 pi on 6 is 11 pi on 6. Again, making sure any fractions are simplified. 3/6 is not simplified, so that is pi on 2 and 11 pi on 6. Okay, let's do one more. There's going to be a couple of complications here. So there's quite a bit going on inside. Stick to your process, it's still the same. Okay. The other thing is that it's equal to 0, so we need to think a bit about that exact value. This tends to trip people up, but actually this is easier than usual. Okay, so first step is to get the cos on its own, which it is. There's a lot going on inside it, but there's nothing outside of that. We've got cos of 3 times x minus pi on 4 equal to 0. So there's a bit going on here. There's a dilation change and also a translation, so we are going to need to do a bit of work. Now, next thing we want to think about is exact values. So cos of what equals 0? So this isn't about a triangle, this is about understanding your unit circle. Cos is the x coordinate. Where is the x coordinate? 0. We know that x coordinate 0 here and here. Okay, cos of pi on 2 would be 0, cos of 3 pi on 2 would be 0, cos of 5 pi on 2 would be 0, etc., etc. Okay, so all our solutions are going to be happening up here and down here, rather than sort of, here and here, or here and here, or whatever it might be. Instead, they're actually on the axes. Okay, so then we want to think about what we're going to do. Remember, same thing, whatever comes out of the unit circle is equal to that. Okay, so we need to think about what the domain of that is. Alright, so we're now going to have 3 times x minus pi on 4 equals something. Now, some people like to expand that out. You really don't need to. After that, once you've got all your solutions, you're going to be solving for x. So the first thing you would do in this form to solve for x would be to divide everything by 3. So you'll get x minus pi on 4 equals all those answers divided by 3. And then the next thing you'll do to solve for x will be to add pi on 4, and you'll finally have your solutions that are equal to x. Okay, let's work out what that means for our domain. If we want x to be between 0 and 2 pi, at this line, we want x minus pi on 4 to be between, so we're going to subtract pi on 4 heading up this way. People get confused because, oh, but I want to add pi on 4. Yes, but when you're going this way, you're adding pi on 4. Therefore, when you're going this way, you're subtracting pi on 4. So 0 minus pi on 4 is minus pi on 4. 2 pi minus pi on 4. 2 pi is 8 pi on 4. Minus pi on 4 is 7 pi on 4. And then we want to get back to this bit. We're doing 3 times that. So we're timesing by 3. So negative pi on 4 times 3 is negative 3 pi on 4. And negative 7 pi on 4 times 3, sorry, positive 7 pi on 4 times 3 is 21 pi on 4. Alright, the 3 is essentially, stretching out the domain over which you're going to look by a factor of 3. So with this span from here to here was still 2 pi. All we did was add or subtract. The span from here to here is still 2 pi. We've now tripled it, so the span from here to here is 6 pi. So it's 3 complete laps of the unit circle, okay? So, but it's 3 complete laps of the unit circle, not starting at 0, but starting at negative 3 pi on 4. Okay, so let's think that through. So negative 3 pi on 4 is out here. Okay, so then we're going to travel around to 0. We're going to travel around to pi. That's pi plus pi on 4. We're going around to 2 pi. 3 pi. That's 3 pi plus pi on 4. 3 pi plus pi on 4 is 13 pi on 4. So we've got to do one more lap of the circle from there. That is 4 pi, 5 pi, 5 pi plus pi on 4 is 21 pi on 4. So it's 3 full laps of the circle. This basically tells you how many laps you're going to need to do, but we're not doing them starting at 0. We're starting at negative 3 pi on 4. Okay. Now remember, all our solutions are happening on the y-axis here because cos is equal to 0. So we're going to have 1. Now I'm running out of room here. Let me move my unit circle over. Sorry, I know you can't do that as easily as I can. Let me just drag this. Sorry. Just drag this across. Okay, let's get rid of these. Give ourselves some space. Okay, so our first solution is around here in the negative. So I'm still around here. Let me just get a different color so you can see where I'm pointing. So it's at 0 minus pi on 2. Yeah, so that first solution there is at negative pi on 2. And after that, we're into the positives. That's why I didn't separate it here. It's just that one negative solution, then everything else is positive. Okay, so my next solution is up here at positive pi on 2. My next solution is down here, which is pi plus pi on 2, so that's 3 pi on 2. My next solution is back up to the top. That's at 2 pi plus pi on 2. 2 pi is 4 pi on 2, so it's 5 pi on 2. Again, you can count. We did this previously. 1 pi on 2, so negative pi on 2, 0, 1 pi on 2, 2 pi on 2, 3 pi on 2, 4 pi on 2, 5 pi on 2 is the next solution. 2. 6 pi on 2 is 3 pi, plus another pi on 2 is 7 pi on 2. So 7 pi on 2 is this one around here, and then we've got one more up the top, which will be 8, 9 pi on 2. Okay, now to get from here to here, we need to divide by 3. Okay, so we're dividing everything by 3, so they're all going to become over 6. So it's minus pi on 6, plus pi on 6. 3 pi on 6. Now I know that will simplify, but it's easier given that we've still got another step to do at the next stage to keep everything on the same denominator. So 3 pi on 6, 5 pi on 6, 7 pi on 6, and 9 pi on 6. And again, I know that will simplify at the end. Okay, I'm going to add an extra line of working in here just to help me. So I'm just going to move that line down, because what I'm going to think about here is getting a common denominator. So I'm going to need to add pi on 4. Okay, so I next need to go from here to here, I need to add pi on 4. So I'm going to need to add pi on 4 to every one of these solutions. So if I'm going to add pi on 4 to pi on 6, I'm going to need a common denominator. The lowest common denominator would be 12. So I'm going to take a moment here just to make my life easier to write a line where everything has a denominator of 12. So pi on 4 is 3 pi on 12. This is minus 2 pi on 12, positive 2 pi on 12, 6 pi on 12, 10 pi on 12, 14 pi on 12, and 18 pi on 12. So now if we add 3 pi on 12 onto each of those, and this is why I keep the denominators the same, don't simplify the fractions as you go, simplify them at the end if you need to. So adding 3 pi on 12, negative 2 pi on 12 plus 3 pi on 12 is 1 pi on 12. So that's where, okay, this solution seems, well, it's negative, that's not in that domain, but by the time we manipulate it, pi on 12 is within the domain. Okay, and that's where if you're not careful about your domain at the beginning, you'll miss solutions. Okay, so so next solution is 2 pi on 12 plus 3 pi on 12, so that's 5 pi on 12. 6 pi on 12 plus 3 pi on 12 is 9 pi on 12. I'm going to simplify that fraction as I go. So 9 on 12 is 3 pi on 4. 10 pi on 12 plus 3 pi on 12 is 13 pi on 12. That doesn't simplify. 14 pi on 12 plus 3 pi on 12 is 17 pi on 12. That doesn't simplify. 18 pi on 12 plus 3 pi on 12 is 21 pi on 12. 3 is a common factor there. So dividing by 3 is 7 pi on 4. And again, we've got all of our solutions. You should be able to check that by solving using your CAS, just check that we found the valid solutions. I know that seems like a lot of work. Sometimes there'll be a lot of solutions, but there's a lot of pattern to them. Yes, you have to write out solutions, but it's also not overly complicated. Really try and stick to the process, get the sine or the cos on its own. What is the exact value? Where are the solutions? Hence, where are my solutions in the unit circle? What do I know about my domain? Do I need to make some adjustment so that when I finally get to my solutions for x, they are all between whatever my domain is. Little note there about solving trig equations using your CAS. We've talked about that. And the work today is from a worksheet that I'll give out, and that's also available to you on Canvas. There's one question that comes from the exercise, and then there is a series of additional questions dealing with these more complicated trig equations where you have to think about that adjustment to the domain.